Okay, so this is the lecture video for day 9. Hopefully you're watching this before class on Friday. In this video, we're talking about multiple regression, which on its face can seem like a kind of complicated extra thing on top of the linear regression that we've been talking about. But hopefully by the end of this, you'll agree that it isn't really that much more complicated than single regression. It's just adding in extra variables. Okay, so what is multiple regression? Well, first let's just refresh what we mean by single regression. And the idea behind single regression is that if we have two quantitative variables that have some linear relationship, maybe we can come up with a line that describes the relationship between the two. In other words, we're looking for a model that we typically call y hat equals some constant plus some variable. Okay, so the idea is that we're looking for a line. The general form of a line is y equals mx plus b. We're renaming some things because, well, when we're adding more variables, we don't want to have m and n and o and extra letters like that. So we're just calling all of the coefficients b. Anyway, that's single regression. The idea is that this can predict or come up with some sort of model that talks about what one variable, the response variable, looks like depending on a single input or explanatory variable. For example, maybe we're talking about how tall a tree is based off of the diameter of its trunk. However, maybe we have some more information available to us. Maybe there's another variable that we can include to get a better estimate for the height. Maybe if we also know the tree's age, then age in conjunction with trunk diameter might actually give us a more fine-tuned estimate for what the total height is. So multiple regression is going to basically be the same thing. We're looking for some sort of model that depends on the other variables. But now, rather than stopping here, we're going to say, oh, well, what if we also maybe had a second explanatory variable, or a third, or any number? We're typically going to stick with 2, but all of this applies to really as many extra quantitative variables as you want to help describe what's going on. In this next example, we'll use quantitative variables like a house's square footage or how many bedrooms it has in order to predict or model what we expect the price to be. In general, we would expect a bigger house to cost more, and so we want to use that idea in order to come up with some sort of model to say, all right, what exactly does this trend look like? Okay, so let's start off by comparing the square footage of a house to the price. And this is from a data set taken, I believe, from Zillow. And the idea is that, well, our intuition is that a larger house, so something with a higher X value, would correspond to a more expensive house. And that certainly appears to be true. So this is a linear model for this picture. In order to check to make sure that a linear model is a reasonable fit, we should take a look at the residual plot. And yes, there's definitely some clustering down here. And perhaps doing some sort of rescaling would be a good idea. Maybe taking the log of the prices. But we're just going to move forward, and because this, I think, is a reasonable residual plot, indicating that a linear model actually somewhat makes sense. Okay, so one other thing I wanted to point out was we can also run summary of that residual plot. So up here we called regression 1 is the linear model of associating price and square footage. So scrolling back down, we ran that the correlation between these two ended up being 0.648. Cool. So that's our R number. If we wanted some more information, we can run summary of this, and it's going to give us sort of the whole readout. A couple things I want to point out is that right here and right here is where it tells us what the equation for the line is. So the equation for this regression line is y hat equals 65,000 plus 202 times the square footage. Don't worry about the other components like the t-value and the p-value right now, or the standard error of this. We'll get to those ideas later. I also wanted to point out that it includes the r squared number. So here we have r squared is 0.420. Up here we found the correlation was 0.648. This number squared should be the same thing as our r squared value according to the summary. Cool. Okay, so as we see, there is a positive association between housing square footage and housing price. As it looks, if we also want to look at the bedrooms is still a quantitative variable. We can talk about the association between the number of bedrooms and the price. And we can do exactly what we just did. We can fit a linear model, which has a reasonable looking residual plot. And then we can talk about what this slope means. So this has a positive slope, meaning that in general, houses that have more bedrooms are more expensive. Okay, so what we want to do is we want to put these ideas together. If rather than just having the information about bedrooms, which isn't a great indicator of price, if you have a 3-bedroom house, it could really be one of many different values. So we want to put this together with square footage to hopefully get an even better model, maybe one with an even better r squared value. In order to do that, we're going to use multiple regression. So the idea is that we're just going to use both of these variables, the housing square footage and the number of bedrooms, as predictors, as things that will influence what our linear model looks like. So here I'm defining, rather than REG1 or REG2, this is REG multiple, and this is the linear model of the housing price compared to, and then we write one variable plus the other variable. And then the result, or this thing, is going to be this linear model. So we can look at what our output is. Well, we have our y-intercept, our coefficient in front of the square footage variable, our coefficient in front of the bedrooms variable. And then we can also look down here and see, hey, this is our r squared value, which 0.435 is bigger than our previous r squared value. So in that sense, this is going to be a better model than using square footage alone. Okay. One thing that should look a little bit surprising here. The coefficient for the in front of the bedrooms terms is negative, which means that according to this multiple regression model, having more bedrooms means the price should actually be lower, which should seem surprising because we had previously, just a minute ago, said that if we're doing a single regression between bedrooms and price, that there is a positive association. More bedrooms means it's more expensive. Why, in this multiple regression, is this coefficient negative, indicating a negative relationship between these two? The distinction here is that for the multiple regression, we're not just saying that houses that have more bedrooms cost less. What instead we're saying is, for a particular square footage, if a house has more bedrooms, it costs less. All right, so imagine you've got a fairly large house. If it's a large house that has a dozen bedrooms all sort of packed in it, we might imagine that that is a lower cost house than if we had the exact same size where a lot of the living space was dedicated to living rooms and libraries and other, high-end features for houses. So the distinction we're making here is for a given size, the fewer bedrooms you have, the more expensive it is. Or at least that's what this model is telling us. One problem with multiple regression is that it becomes really difficult to see. With our single regression, we can make a plot where the x-axis is our explanatory variable, the y-axis is our response variable, and we can draw a line, we have our scatter plot, and we can go from there. For the multiple regression, especially when we get up to more than 2 explanatory variables, all of a sudden we're talking about a 4 or 5 or 6 dimensional picture, which doesn't really make any sense. That said, for 2 explanatory variables, we can have a 3-dimensional picture. And so the code that goes into making such a picture is definitely not something that I expect most of this class to do. It's included in the R Markdown file if you'd like to take a look, but it's certainly not expected that you care at all about how exactly I made this picture here. So what we have is a 3-dimensional plotly plot, which is comparing bedrooms and square footage as our explanatory variables to price. And so the scatter plot should be, each of these points corresponds to one of our data points. And the plane is corresponding to the linear model. A single regression linear model is going to be a line. A multiple regression linear model is going to be a plane or a higher dimensional version of it. But what this linear model is saying is that for a given square footage and for a given bedroom count, we expect the price to be a certain amount. This is the expected value. Any given house is almost always going to be something different than that. We can still do things like calculate the residuals or look at the R-squared value and do all of those types of things, even if looking at a picture is less of a valid tool. That said, we do have this 3D plot, and I wanted to point out a couple features of it. The first is that if we're just comparing square footage to price, then then as the square footage increases, let's take a look at that. If you spin it around too much, it gets a little confused. Okay, so we're comparing square footage to price, and as the square footage increases, the model is expecting the price to increase, which makes sense. However, if we look at bedrooms, so the bedroom count, as the number of bedrooms increases, we actually expect the price to decrease. And this is getting the image to cooperate can be a little bit tricky, but in general we have this downward slope. And the dominant effect here is that square footage is really what's governing what's going on. At a given particular square footage, we may expect more bedrooms to mean a lower price. One main takeaway that I want you to have from this is that when it comes to multiple regression, just because one of the variables has a positive association with our response variable doesn't necessarily mean that when we take multiple explanatory variables into account, that relationship will still be positive. It's certainly plausible for another explanatory variable to have sort of a more dominant effect, and for our original explanatory variable to maybe even have a 0 or a negative association or coefficient when we look at this multiple regression model.